Welcome. So let's continue our discussion of chapter 5 by getting into a concept known as induction. So induction is a great way to leverage recursive sequences. So the idea of the mathematical principle of induction is that we are going to essentially set up dominoes to knock everything down. But let me kind of set up the basics and then I'll come back to it. So the principle of mathematical induction means I start with some p sub n, where this is a parameter at n. So it's gonna be a function. It's usually a sequence is what we're predominantly going to work on, but something at n value and takes on non-negative integer values. So that means we can start at 0 and it can start at 1. A lot of different situations. Again, you got to pay attention to the particulars. The way an induction proof basically goes is it uses three main things. Number one, a base case. This is the smallest n value that we can think up. Then we state an induction hypothesis, which is a general statement of when n equals some k. We say suppose it's true for some k value, and then we show that because of that, we now look at the next step and show that the next step is true. So here's the idea behind all this from a domino standpoint. And I'm just going to draw down here. So let's suppose that something is true for 1. Let's suppose that 1 is true. Well, if I say if it's true for k, that means it's true for, if it's true for k, it means it's true for k plus 1. That is what this portion is proving. Whereas the base case would be showing this part. But wait, suppose I've shown that all of this is true. If it's true for 1, then by this, that means it has to be true for the next number, which is 2. But if it's true for 2, it has to be true for 3. If it's true for 3, it has to be true for 4. And it just keeps on going forever because we've now shown that everything automatically proves it's true for the very next step. So this is why the principle of mathematical induction is really, really cool. Is essentially you're going to take small cases and use those to prove a very, very big general situation. Let me demonstrate this with a really nice example. We're going to show this summation is true. So again, this is the comment that I just said, but I'm going to show you for this example. I'm using summation. Now, my summation notation is a little bit different just because formatting of different things, but this is my lower index, and notice my index variable for my summation is j. And I'm saying I want that true for n bigger than or equal to 1. Well, that makes sense. It doesn't make sense if j is 1, j can be anything less than can be 0. Okay, so let's start at least at 1. And I'm saying the sum from 1 all the way up to n of 2j minus 1 is equal to n squared. That is my claim. So we have to start by saying, what is my base case? Well, our base case would be the smallest n value, which would be n is 1. Now I'm simply going to show that when n is 1, that my summation happens equal 1 squared. Well, that's going to be 2, because it's just the 1 situation. This is going to be 2 times 1 minus 1, which is 1. We do all the arithmetic, which happens to equal 1 squared. So therefore, our base case is true because we showed that our formula, so again, we showed that our formula was true in the situation when n is equal to 1. So what you're going to do, what you're trying to do is you're trying to show that this equals this. So you have to start with one side and then show that it's equal to the other side. Some way of continually moving from one side to the other. You could have started with the n squared and moved your way back, but usually that doesn't really work super well. I'm just being honest. All right, so that was our first step. That was our base case. Remember, the next thing we have to do is induction hypothesis. So we state that this is true for some k value. So in other words, at some k value, we know this is true. So notice I'm saying n is equal to k. I'm replacing the n, because the n is the general term, with just some unknown but supposedly fixed k value. Now I want to show that this is true when n is k plus 1. In other words, let's look at the next one. So if we come to this case, we're now looking at the summation that starts at k plus 1. Well, remember when we talked about summations, we can peel off the k plus 1 term. So this right here is the sum, is this is the sum up to k, and this is the k plus 1 term. We broke it off where we just plugged in the k plus 1. Well, but wait, we know that by our induction hypothesis, so let me add a little note here. I should have written this down. This is by our induction hypothesis. We know that this summation right here is equal to k squared. Remember, that's what we were assuming was true. But we were saying that if that was true, we're essentially showing that the k plus 1 situation is true. Well, now I have this big, giant, long thing. So let's do a little bit of math. Let's do some algebra. Let's multiply this out. So if I multiply out the 2, so this would be by just, so let me write down what I'm doing. This first line, let me erase this stuff. So my first line was breaking off the last term. Again, this is a proof, so we want to kind of illustrate this. This is by distributing, and this is by grouping or combining like terms, whatever you want to say. So I now have this terminology right here. But in case any of you don't remember from your algebra days, that quite simply turns into k plus 1 squared if you factor it. So that's by factoring. Wait a second. We wanted to show that this thing was equal to k plus 1 squared, because remember, we want to show that when it sums up to some value that's equal to that value squared. So we've done it. We've shown that this is true, that when it's true for k, it's also true for k plus 1. So by the principle of mathematical induction, it's always true. We have now proven it, and we get this so powerfully. So the idea here is that we get to use mathematical induction because we assumed it was true for k and showed that that meant it had to be true for k plus 1. But since we already showed a starting value for which it started, boom, 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 boom. All right, so this is the really cool part. Let's do another example because I want you to kind of see a different one. This is an inequality example. I want to show that n factorial, it is bigger than 2 to the n whenever n is bigger than or equal to 4. So I would love it if you just took a second and thought about this for yourself. What is your base case? Go ahead and pause the video, think about the base case, and try to do your base case. All right, so if you did this, the base case should have been when n is equal to 4 because that's the smallest n value. We want to pick the smallest n value. You could not do this for n equals 1. It's not true. So you have to pick the small, you have to look at what is my domain. In this case, it was starting at 4. If I plug in 4 factorial equals 4 times 3 times 2 times 1, which is 24, which is bigger than 16, which is 2 to the 4. I know we talked in proofs about wanting to do these things vertically. Horizontally like this, it does work a little bit for these inequalities because you have this chunk, which is equal, inequality equal. So it kind of tends to work out a little better with inequalities to make this look. I'm just saying you don't have to do it, but just kind of hold on. All right, so that's what your base case should look like. Now, next question. What is your induction hypothesis? Well, remember, your induction hypothesis is that it's for some n equals k, the k factorial is bigger than 2 to the k. And we now want to look at when n equals k plus 1. Warning though, I cannot start with my inequality. If I start, just like on the previous step, I could not start with my equality. I have to start with one side of the inequality and go to the other side of the inequality. That is where this becomes hard. So if you ever start, if you're like induction hypothesis, boom, I'm already assuming it's equal and we're going to cancel stuff out. That is actually circular. You're already getting yourself in trouble. I'm just telling you right now, do not do that. Okay. So in this case, I would say k plus 1 factorial is equal to k factorial plus k plus 1. That's using the definition of factorials. But k factorial times k plus 1 is bigger than 2 to the k times k. I could have even made this k plus 1, but I made this even smaller. The reason being because we know that k factorial is bigger than 2 to the k, and k plus 1 is bigger than k. So since both of these products, both things we're multiplying on the right-hand side are smaller than both of the things we're multiplying on the left-hand side, the right-hand side is smaller. Well, now let's look at 2 to the k times k. Well, k, remember k has to be some number bigger than or equal to 4. So this is bigger than 2 since k has to be bigger than 2. But this thing right here, 2 to the k times 2, is equal to 2 to the k plus 1. That's by our definition of rules. Wait. So let's go back to this. K plus 1 factorial is equal to k factorial was equal to this, which was bigger than this, which was bigger than this, which was equal to this. That means we put them all together, we get the inequality that we really want, namely that k plus 1 factorial is bigger than 2 to the k plus 1. Because notice all the inequalities are flowing in the same direction. We're going from the left, I was to the left, I modified it. Then I moved more to the right. Then I moved more to the right, moved more to the right. So we're able to maintain the inequality as we pass through all these things. There's multiple inequalities that I actually had to go through on this step. It's part of what makes this kind of proof a little bit more challenging. All right. I hope that example helps. Let me know what questions you have. Good luck.